Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Minimum number of operations to sort a binary tree by label. Leetcode 2471. In this problem, we are given root of the binary tree with unique values. In one operation, we can choose any two nodes at the same label and swap their values. And we have to return the minimum number of operations needed to make the values at each label sorted in a strictly increasing order. The label of a node is the number of edges along the path between it and the root node. Then in example 1, for the given tree, we have 4 labels, label 0, label 1, label 2 and label 3. At label 0, we only have node 1, and since there is only one node, it is already sorted. So minimum number of swaps we perform at this level is 0. Then at level 2, node values are 4 and 3, which is not in ascending order. So to sort it, we need to swap the values 4 and 3, resulting in the sorted array 3, 4. And this requires exactly one swap. So minimum number of swaps for this level will be equal to 1. Then for the next level, node values are 7, 6, 8 and 5. And this list is also not in ascending order. And sorted version of this list will be 5, 6, 7, 8, which we can get by swapping 5 and 7 first, which will give us 5, 6, 8, 7. And then we swap 8 and 7, which will give us this sorted list. So minimum number of swaps required at this level are 2. And finally at the last level, nodes are 9 and 10, which are already sorted. So minimum number of swaps required here are 0. So total number of minimum swaps required to make the values at each level sorted is 1 plus 2, which is equal to 3. Now in terms of solution, since we want to perform the swap operations on the nodes at the same level, to make each level sorted in a strictly increasing order, we need to perform level order traversal. So first we will perform level order traversal on the binary tree and collect the nodes at each level into an array or array list, and then count the minimum number of swaps required to sort each list, and sum of all those counts will be our answer. I have already covered level order traversal level by level on this channel. So if you are interested in learning or revising it, please check out the I button. After performing the level order traversal, we collect the node values into separate array. Let's focus on level 2, where the node values are 7, 6, 8, 5. And we have to find minimum number of swaps required to make it sorted. So let's look at the sorted list as well. It will be 5, 6, 7, 8. And one way to find minimum number of swaps is by using cycle sort, but I will cover it in the dedicated video later. For this problem, we will explore even more straightforward approach. Let's look at the first position in both the arrays. First number in sorted array is 5, but in the original array is 7. So should we swap or not? And the answer is we should, because 5 should be the first number. So we swap 5 with number 7. That is, we swap the numbers at index 0 and index 3. Now we have a small problem here, that when we search for 5 in the original array to perform a swap, it will take O of n time, where n is number of elements in the array for the current level, because we are going through each index in the array and checking if the number is 5 or not. So this time complexity is super high. And which data structure can help us speed it up? Answer is hash map, as it reduces the lookup time complexity to O of 1. And in this problem, it is given that binary tree has unique values, making sorting and counting swaps easier. So we can store these values in the hash map without any collisions. So let's pre-process the array and store number to index mapping in the hash map. So for the original list, number 7 will map to index 0, 6 will map to index 1, 8 will map to index 2, and 5 will map to index 3. So now we can easily swap numbers 5 and 7, as we get the index of 5 in O of 1 time, which is 3. But now after the swap, we should also update correct indices of 5 and 7 in the hash map to maintain consistency. So after the swap, the array becomes 5, 6, 8, 7, and index for 7 becomes 3 and index for 5 becomes 0. Note that we don't need to correct the index for value 5 in the hash map, as we have already processed the 0th index, but we will still do it just for the sake of consistency. Then we move to the next index, which contains value 6 in both sorted and original array. So that means 6 is already at the correct position. Then we check the numbers at index 2, and we can see that in the sorted array we have number 7, but in the original array it is 8. So that means you have to swap this number 8 with the number 7 in the array. And for number 7, we can see that the index is 3. So we swap them. And now our array becomes 5, 6, 7, 8. And the updated indices will become 2 for number 7 and 3 for number 8. And finally, at the last index, that is index 3, we can see that 8 is already at the right position. So we don't have to make any swaps. And now we are done with all the positions and the list is sorted, and minimum number of swaps we performed is equal to 2 for this level. Similarly, we will run this algorithm for different levels, and total number of minimum swaps at each level will be our answer. Now let's jump into the code part. First, let's initialize answer variable to store total number of minimum swaps needed. Let's initialize queue to perform label order or BFS traversal. We can use linked list implementation in Java for that. Let's add root node to the queue. Now we will start the BFS. So while queue is not empty, get the current size of the queue, indicating number of nodes at the current level. We will create a list to store the values of the nodes at the current level. Also, we will use the array list implementation here, because then we can use the indices to easily swap the values. Now, for each node at the current level, we will dequeue the node, add the node value to the current level list. And if the node has left and right children, we will add them to the queue. And once we are done with this level, we will make a call to minswaps helper function and pass current values array list to it and add the number of minimum swaps for the current level to our answer. And once we are done with BFS, we will return our answer. Now let's define minimum swaps helper function. It takes list of values in the binary tree at a given level and returns minimum number of swaps to make it sorted. Let's get the length of the array so that we can loop through array indices. Let's also create a hash map to store number to index mapping for each number in the given array. Now we will loop through the array and map the value at index I to its index and store it in the hash map. Let's also create a copy of the original array and sort it. Let's also define number of minimum swaps for this level, and initially it will be equal to 0. Now we will iterate through each element in the given array and compare it with those in sorted array. If current element is not in the correct position in the sorted array, that is, element at ith index in the original array is not equal to element at ith index in the sorted array, then we need to perform the swaps. So we should increment number of swaps by 1 and swap these values. So let A be the current element in the original array and B be corresponding element in the sorted array. Then we will set the value A at the index where B was originally located, and we can get the position of B from number to index map. Let's also update the hash map to reflect the new position of A. Let's also set the correctly sorted value B at the current index in the original array and update the hash map to reflect the new index of B. And once we are done with all the numbers, we will return swaps as our answer. Now we are done with both the functions, so let's submit this code. Cool. In terms of time complexity, it will be O of n log n, where n is the number of nodes in the binary tree. Because when we run the BFS, that takes O of n time, as we are visiting each node only once. And then for each level, we are building number to index map, which takes O of k time, where k is number of nodes at that given level. And then we are making a copy and sorting that copy. That takes O of k log k, and k is proportional to n. For example, for the completely filled binary tree, in the last level there will be n by 2 nodes. So, because of this, the time complexity is O of n log n. And in terms of space complexity, it will be O of n, because we are storing the node values in the queue and then in the respective level arrays. And for each level, we are also storing number to index hash map as well as sorted array copy. So because of this, the space complexity is O of n. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.